Hi, what you're looking at is uraninite, the ore of uranium. Now, normally we wouldn't see uranium in this concentration in a rock. Most often we find it as tiny little, almost trace elements within particularly igneous rocks. What this mineral will allow us to do, though, is to date the rock that we find it in. So what I want to do in this lesson is try and apply our understanding of radiometric dating that we covered last lesson into a number of different situations. Let's start with this. This is the graph you can see on page 20 of your theme 9 booklet. What we have here are decay curves. They're different because these different elements that are listed have different half-lives. You can see that the horizontal axis here is actually time in millions of years, rather than just number of half-lives. If we plotted this by number of half-lives, each of these curves would look the same. But because we're using actual time, we can start to work out a few other things about this, or about the decay of these elements. Before I set you off to have a go at question 13, let me show you this. On the vertical axis here, we have the percentage of radioactive isotopes. So it's the percentage of parent atoms. So at 50% on that scale, so that horizontal green line I've drawn, that represents one half-life. Knowing that, what I'd like you to do is have a go at question 13 on page 20 of your booklets. Press pause and have a go at that now. Okay, let's see what you've come up with. So with this graph, the first question you asked was, which element has the longest half-life? And it's thorium. If we follow that line across at 50%, we can see that thorium has a half-life of about 14,000 million years. I then asked you to work out how many half-lives each element has been through. So uranium-235 there has been through 5 half-lives. That's because that line, the red line on the graph there, goes through 50% for one half-life, 25% for 2 half-lives, 12.5% for 3, 6.25% for 4, and it ends up at 3.125% for 5 half-lives. Uranium-235 gets down to 6.25 there, so it's been through 4 half-lives. And thorium-232 has only been through 1 complete half-life. It hasn't decayed enough, there isn't enough time shown on that graph for it to have decayed through 2 half-lives. The final question then, which of these is most useful for dating things that have happened on Earth? Uranium-238 gives us perhaps the best compromise between these. Okay. Let's think about how else we could approach this same idea. We can count the number of elements within a mineral of parent and daughter. So if you have a mineral that has a half-life of 200 million years, and you count 1 million atoms of parent and 1 million atoms of daughter, that means the balance between the two is 50-50. 50% parent, 50% daughter. Therefore, that mineral has been through 1 half-life of decay. So in this particular case, it'd be 200 million years. Okay. If we have a look at page 21, question 14, we have here a table for you to fill out. There's some description then of the minerals in each sample. Let me start you off with mineral A. Now, mineral A, we're told there are 500 million atoms of parent, 1500 million atoms of daughter. So the number of atoms before decay has got to be those two added together. Whenever we look at the parent and daughter atoms, the two of them added together is what we start with. It says we have a half-life of 200 million years. So after one half-life, we're going to see 1,000 million parent and 1,000 million daughter. So with the half-life then of 200 million years, that's going to be 200 million years of time. After two half-lives, we halve the number of parents again. So now we only have 500 million. Remember that the parent plus daughter atoms must equal what we start with. Okay, I've got you started there. What I'd like you to do now is complete the rest of that table. What can we work out about? Press pause now, see what you come up with. Okay then, let's see what you've found. So this is our table. We've already filled in some parts of it. So after two half-lives, sample A is going to have 1,500 million atoms. So that's going to be 400 million years. So sample A is going to be 400 million years old. Sample B then, we're told, has 250 million atoms of parent, 1,750 million atoms of daughter. So that's a total again of 2,000 million atoms at the start. Half-life of 300 million years. So we work through in the same way as we did for sample A, except this time, after one half-life, 300 million years have elapsed. Two half-lives then. After 600 million years, we've got 500 million parent, 1,500 million daughter. We still haven't reached the description we have though at the start. If we go through another half-life then, we're now down to 250 million parent, 1,750 million daughter, so we've been through three half-lives, which is 900 million years. Finally, specimen C. If we add the parent and daughter there, we end up with 6,000 million atoms, a half-life of 1,200 million years. So after one half-life, 50-50 split, 3,000 million atoms of parent and daughter. After two half-lives, again we halve that, so that's 1,500 million parent, 4,500 million daughter, which is where we are with the description. So it's been through two half-lives, and that's 2,400 million years old. Okay, we can see then that we can apply this understanding in a number of different ways, either by working out proportions or using the decay curve graphs in a slightly different way. What we need to do next time is to start thinking about how we can actually use this to work out the age of the Earth. I'll see you then.